So exercise momentum. We'll solve some questions related to this exercise. The topic is done. The explanation of the topic, like what you have in this topic, you should first know the concept of the momentum, which is a product of mass and speed, velocity, and then the impulse, which is a change in momentum. You can find the impulse by taking a difference or using a vector diagram or by using a product of force and time. Sometimes you may have a graph between a force and time. So you use area under the graph to work out the impulse. And then we have a conservation of the momentum, which is the momentum before equals to momentum after. And then you have a conservation of momentum in 2 dimension, but that is only for Cambridge student, not for the edX. So example, two objects are traveling directly towards each other and they collide. Object A is having a mass of 2 kilograms initially traveling to the right, and object B is a mass of 5 kilograms initially traveling to the left at a speed of 2 meters per second. What is the total momentum of A and B after collision? Yes, you can use the chat to answer this question. What is the total momentum after collision? I will explain that, but I want student to participate. Use the chat to answer what should be the right answer for this. So we use a conservation of the momentum. The two objects traveling directly towards each other. An object A is having a mass of 2 kilograms, which is moving towards the right-hand side with a speed of 3 meters per second. And object B is having a mass of 5 kilograms, which is moving towards the left at a speed of 2 meters per second. So according to conservation of the momentum, the sum of the momentum before should be equals to sum of the momentum after. What is a momentum before collision? If one of the side, like example, if the right-hand side you took as positive direction, the left-hand side you will take as negative. So 2 multiplied by 3, this will be 6 kilogram meters per second. What is the momentum here? 2 multiplied by 5, that will be 10 kilogram meter per second. But what is the direction? Opposite. So what is the total before? The total before is 6 plus 6 and minus 10. So plus 6 and minus 10 is minus 4. So means the momentum after should be minus 4. So means either A can be an answer or B can be an answer. But what is the direction? Because we are getting a negative answer, what does it mean? It should be A. Is it clear? So when two objects are colliding with each other, the total momentum before must be equal to total momentum after. So the momentum before was negative 4. So according to principle of conservation of the momentum, momentum after should also be negative 4. And negative 4 means what? Negative 4 means negative sign shows as we took the right-hand side direction as positive. So the left-hand direction will be negative. The photograph shows a fireboat used to put out fires on ships at sea. A pump fixed on the boat to the boat pumps the water from the sea. The seawater is projected at a high speed out of the pipe connected to the pump. The mass of the seawater pumped each second is 300 kg. The pipe has a diameter of 10 centimeter. The density of a water is 1030 kilograms per meter cube. Show that the speed at which the seawater is projected from the pipe is about 4 meters per second. So we want to work out the speed at which. So what is speed? Speed is distance divided by time. Okay. That is what actually the speed is. And the speed at which the seawater projected from the pipe is about 37 meters per second. Means it will cover 37 meters every second. So we need the speed. But what are the things we have? We have the mass, we have the density, and we have the diameter of the pipe, the size of the pipe. Okay. Now, how it can be done? And one more thing, as you can see about the information about the this is a mass of a seawater which is pumped every second. So this is not only the mass, this is mass per second, or m by t. Okay. So this is mass per second, or m by t, which is 300 kilogram per second, because it's written here each second. Now I want to modify my formula according to this. So instead of distance, if I say velocity is length over time, like what length the water covered divided by time, I will know the velocity. What about the length? We have the formula that volume is area multiplied by length. That's a formula for volume. So what about the length? The length is volume divided by area. So volume is divided by area. What we get? We get length. So means in place of this length, what I can write, because this V is the volume, I will use another color. This V is the volume, the red, and the V in blue is the velocity. Velocity is distance divided by time. But I don't have the distance. So I need how much length this water will cover. If I know this length, the water cover, I can work out the velocity. But the things what I have the density and I have the area. I have the diameter. So from diameter, I can work out the area. So in place of this length, I can substitute volume divided by area into T. Is it clear? The modification of the formula? Anyone having a question or a doubt till this point? So in place of length, what I wrote volume over area. Because the total volume of the water which is coming out is area multiplied by length. And length is actually the distance which this water will cover. Yeah, I'm coming to that point. How we'll get the volume and area? Now, how to get the volume? You have the mass and you have the density. So if you have the mass and density, what we can use? We have the formula density is mass over volume. So the volume will be equals to mass divided by density. So in place of volume, I can substitute mass divided by density. So I will have a formula now that mass divided by density into area into time. Is it clear? So what about the mass? I have the mass, which is 300. I have the density, which is 1030. I have the area. How to get the area of the cross section? Because I have a diameter. So if I have a diameter of a pipe, I can work out the cross sectional area, which is pi r square or pi d square by 4. If I have a diameter, it will be pi d square by 4. If I have the radius, I will use pi r square. I can just divide the diameter by 2 and use this formula. But keep one thing in mind, this is given in centimeters, so I have to convert into meters. So time is 1 second, each second is there. So we have the mass, we'll get the area and the density. So we'll work out the speed or the velocity at which this water is coming out from the pipe. Is it clear, this question? Or should I repeat? So 37.08 meters per second. Is it clear or should I repeat?
No, Jackie.
Okay, sure. For some students, I'll repeat. Look, the question is, yeah, I will repeat the question. See, the question is, we want to show that the seawater is pumped at a speed of 37 meters per second. That we have to show. But the thing is, if you need the speed, you need the distance, and you need the time. But what you know that the mass which is coming out, you know the density of the seawater. So from mass and density, you can work out what volume is coming out from the pipe. That is one thing. So we'll get the volume which is coming out from the pipe, because density is mass over volume. So volume is mass divided by density. We have the cross-sectional area. We have the cross-sectional area because we have a diameter. From a diameter means we have the cross-sectional area. So we can simply work out how much, if we have a certain volume of the liquid, how much length it will cover every second, or what length will be there, or what distance this water will cover. Because we know, like example, how much water is there, and we know the cross-sectional area. So we can identify that what will be the length covered by this object, this amount of a water, if we know the area. That's why, like example, if I have a constant mass, if I have a constant volume, and I have two pipes, one is a narrow. If I have the same amount, same volume is coming out, but if one pipe is a narrow, smaller cross-sectional area, so the speed at which the water is coming out will be higher. Why? Because the water will cover a greater distance here. But if I have a large cross-sectional area and I have a constant volume, so the speed at which the water will come out is smaller, or it will cover a smaller length or a distance. So using the volume and the area, I can work out what length it will cover, because we have the formula that volume is area multiplied by length. So volume divided by area will be equals to length. And the speed is equals to length divided by time. So length is volume into area. So volume into area divided by length is volume divided by area. So volume divided by area into time. And volume itself, because we have the mass and density, so volume is mass divided by density. So we'll substitute in place of volume mass over density. And we get what speed the water will come out. Yes, Saud, any doubt? Any question or doubt in this? Okay. The next is determine the rate at which the momentum of a seawater is changed by the pump. You may assume that the seawater was initially stationary. So rate of change in momentum. Rate of change in momentum means like change in momentum divided by time. Change in momentum divided by time means force. Rate of change in momentum is actually known as the force as well. So you need the force. Or you can also use this formula. M is a mass of a water which is coming out 300. And what speed it was coming out? We worked out 37. What was the initial speed? The initial speed is 0. And what was the time? Because every second, how much water was coming out? 300 kilogram. So the time was actually 1 second. So 300 into 37. And what I will write the unit? I will write the unit as Newton. Why Newton? So it will be 11,100 Newton. So 11,100 Newton will be the rate of change in momentum, or you can also say the force. The projecting water from the pipe causes a force to be exerted on the pump. Explain the direction of the force on the pump. Like here, example is a pump. What is the direction of the force on the pump? What is the direction of the force on the pump? Regarding the previous question, look in the question, it was rate of change in momentum. The question was rate of change in momentum. Rate of change in momentum is actually equals to force. If it was only change of momentum, then it is not force, it is impulse. But the rate of change in momentum, which is the force, because it is mv minus mu divided by t. That is, rate of change in momentum is a force, but change in momentum is an impulse. So what will be the direction of the force on the pump? The water is projected having a force in this direction. What will the direction of the force? So it will be in opposite direction, like if a water is projected at a, so the direction of the force is opposite. Force on the pump will be opposite to the direction of the motion of the water. And according, you will mention according to Newton third law, it will be a pair force. In part C, initially the pump is turned off and the fireboat moves forward through the water at a constant speed. The boat engines provide a constant forward force, okay? When the pump is turned on, the water is projected forward and the fireboat slow to a lower constant speed. Explain why the boat now has a lower constant speed. You should refer all the horizontal forces acting on the boat. So what will happen? Like example, say this is a fireboat which is moving at a constant speed in this direction, okay? Initially, when the pump was off. Then what they are saying, when the pump is on, the fireboat slow down to a lower constant speed. So what actually happened? So according to Newton pair forces, there will be force on the water, there will be equal opposite force on the pump. And that force is same as the force on the boat. And as a result, what will happen? There's a driving force is there, and there's a driving force and the opposite force is there. Because of Newton pair force, opposite force is there. So as a result, what will happen? These two forces, first, why it slow down? So first, why it slow down? When the pump is on, it means this driving force is less than the force due, the reaction force due to on the pump. That's why initially it will slow down, because the direction of the resultant force is opposite to the direction of the motion. And when the boat slow down, what actually happened? The resistive force from the water also decreases, because right now water, when initially when the pump was off, there were two forces which are acting. One is the driving force and one is the drag force from the water. And both were balanced. As the both were balanced, it was moving at a constant speed. Okay. So the driving force and the drag force both were balanced and it was moving at a constant speed, and the pump was off. Then what happened? When we switch on the pump, according to Newton pair forces, there will be force on the water, equal reaction force will be there, and that is same as, that will be same as the force on the boat. So as a result, there will be a resultant force which oppose the motion. That's why first initially what will happen? It will slow down. Then why again it reach a constant speed? Because when it slow down, the drag force decreases. Even though the reaction force is the same, but the drag force decreases because the drag force depends on the speed at which the object is moving. So what will happen? Because in that case, the drag force decreases. So the sum of the reaction force and the drag force again become equal to the driving force. So now the boat will move with a constant speed. So three things happen here. First is it was moving at a constant speed because the drag force and the driving force were same initially. When the pump is on, the reaction force on the boat cause a backward resultant force. As a result, the boat will slow down. When the boat slow down, the drag force decreases. So the reaction force plus the drag force again equals to the driving force. So the boat will move with a constant speed, but with a lower constant speed. Is it clear? The driving force is not decreasing, the resultant force is decreasing. So three cases you have for this one. The driving force is not decreasing. First example, say this is a boat. You have the driving force, say 100 Newton. you have the drag force because it was moving. So drag force was also there, 100 Newton. What about the resultant force on this boat? The driving and the drag forces are equal, so there's no resultant force. The boat was moving at a constant speed initially. That is the first case. Then what happened when the pump is switched on? So according to Newton pair force, there will be an equal reaction force. The driving force remain 100. The drag force was 100 that moment. But what happened? A reaction force, the Newton pair force is there. So example, the Newton pair force is 20 Newton. So now what happened? There is a resultant force of 20 Newton opposite to the direction of the motion. Because initially the boat is moving towards right, but there's a resultant force opposite to the direction of the motion. What it will cause? It will cause deceleration. Slow down. As the boat slow down, now what will happen? The drag force depends on the speed of the boat. The driving force still 100 Newton. The reaction force of the pump is still 20. But what happened to the drag force as the speed decreases? The drag force will also decrease. So now the reaction force and the drag force again balance with the driving force. And again, there's no resultant force. So this boat, again, it will move with a constant speed. But if you compare the constant speed initially, it will be higher as compared to a new constant speed. Is it clear? Discussion? Why lower constant speed? Because in this part, the speed has decreased. First, it was like having, say, speed of 30 meters per second. But because there was a resultant force opposite to the direction of the motion, this caused a deceleration. So it was 30 meter per second. Maybe now, because of deceleration, 25 meter per second. And at this 25 meter per second, the drag force decreases and the sum of the drag and the reaction force equals to the driving force. So again, it will move at a constant speed. In question 3, a game is played where each player must use a mallet to hit the disc across the table into the opponent goal. One player accidentally lets go of a mallet, and the mallet travel at a speed of 1.6 meters per second, collide with a stationary disc. After the collision, the mallet continue in the same direction with a speed of 0.3 meter per second. The disc move in the same direction as a mallet with a velocity v. Calculate the velocity v. Assume that the frictional forces are negligible. The mass of the mallet is given and the mass of disc is also given. So whenever objects collide or explode, we use a conservation of the momentum, and this is a conservation of momentum in one dimension. This is a momentum before equals to momentum after. So 0.17, the momentum, the mass of the mallet, and the speed is 1.6. The momentum of the disc is 0. The momentum after, it will be 0.17 and the speed is 0.3. And the mass of the disc is 0.035 multiplied by speed v. So we'll simplify and we'll make the subject v. What's the answer for this? You just have to solve for v. What is the answer for v here? 6.3, yeah, that's right. So The final answer is 6.3 meters per second. So we use the conservation of the momentum. Okay. So the final is 6.3 meters per second. Now, the next part, to reach the goal, the disc must move up a ramp at an angle of 30 to the horizontal. Okay. The velocity of the disc at the bottom of the ramp is 5 meters per second. The disc move up the ramp and the work done by the disc against the frictional force. The disc moves at a distance of 6.5 centimeter up the ramp before moving back. Determine the frictional force. This is actually related to conservation of energy rather than the momentum. I will give you an idea, but our next topic is about work, energy, and power. In that one, I will explain this question in detail. Right now, I will just give you an idea about how it can be done. Look, what actually happen is when it is moving, it will have a kinetic energy at this point, okay? When it is going up, it will have gravitational potential energy, GPE. And because there's some friction, so some of the work it is doing against the friction. So if we use the conservation of the energy, the principle of the conservation of energy, so we'll say the kinetic energy will be equals to the work it did against the friction plus the gravitational potential energy. And kinetic energy will be half mv square. The work done against the friction, work is force into distance, like how much distance it move on the ramp, that will be the distance. F is the friction force we need. D is the distance, which is already given in the question. And potential energy is mgh. So how much height it will cover, we can work out. How we can work out, because if I know the distance here, if I know that this covers certain distance, like say 5 centimeter, and I know the angle, so I can work out what height it will be. So that will be the height. Mass is there, gravity is there, so we can work out the frictional force. So we use the conservation of energy here. The kinetic energy will be equals to work done against the friction plus the gravitational potential. About the calculation in detail, I will do with the work energy topic. Okay. Is it clear? The basic concept about the conservation of energy?
Yes.
Question 4. You can use the chat to answer. A car travel north with a velocity of 50 while still traveling north, the car slows to 20 meters per second. Which of the following is a change in the velocity? Change in the velocity. Which of the following represent the change in the velocity? Use the chat to answer. Which of the following represent the change in the velocity? Look, remember, whenever we need the change in velocity, it's a final minus initial. The initial is 50 and the final is 20. So if I need the change in the velocity, it will be 20 minus 50. So 20 minus 50 is minus 30 meters per second. That's why B should be the right answer. Okay. But how? Okay, yeah. Look, that's a good question. One of the student ask a question like how it is negative if it's still traveling at the north. Look, the first velocity was 50. So we draw a vector 50 meters per second. And the second velocity is 20 meters per second, the same direction. This is the final, this is the initial. When I use a vector diagram, if I use a vector diagram, first I will draw final, because if I need the change, it is final minus initial, okay? So first I will draw the final vector. So I will draw this 20 first. Then I will draw negative of initial. So initial is upward. What is the negative of initial? So the negative of initial will be downward. So the negative of initial, like this is minus u. And this was example V. Now, if I need the resultant, this was my starting point and this is my final point. So when I work out the resultant is always from tail of the first to the head of the last. So tail of the first to the head of the last, when I join, I will get V minus U. So you can clearly see what is the direction of V minus U. The direction of the V minus U is downward. And originally the object is moving towards north, upward. So the direction of the change in the velocity is opposite to the original direction. That's why we got negative 30. Is it clear? Question 5. Use the chat to answer. And I want participation from everyone. Which of the following is a base unit? Which of the following quantity has a SI base unit as kilogram meter square second raised to power negative 3? So when we check the force, F is equals to MA. This will be kilogram and acceleration is meter second raised to power minus 2. No. When we talk about momentum, the product of mass and velocity, so kilogram, ms minus 1, no. When we talk about work, force into distance, force is Newton or kilogram meter second raised to power minus 2, and the distance is meter. So this will be kilogram meter square second raised to power minus 2. So that's not, it's power actually, so C will be the right answer. Because power is work divided by time, work is this. Power is work divided by time. So work is kilogram meter square second raised to power minus 2. And then divided by second, it will go in numerator. So it will become kilogram meter square second raised to power minus 3. The magnitude of the velocity did not change. Which of the following arrow represent the direction of change in velocity? Change in the velocity. Remember, it's important, like the length of this arrow is important, because when you work out the change, you should draw the correct length, like draw it accordingly, same length. Use the chat to answer. The length is important when you draw the correct length. The two are not having the same magnitude. It's a bit different. The length of before and this length is different. I said this length, like example, say this is 3 centimeter. This length is not same. This is 2 centimeter. Example. So lengths are not same. That's what I'm saying. So if the lengths are first, if you need a change, we draw the final first after. So we draw same length, same direction. Then we draw opposite of the initial. If before was upward, opposite will be downward. So what about the resultant from tail of the first to the head of the last? That will be the resultant. So it match with option B. So this is final, this is negative initial, and this is the change in the velocity, which is final minus initial. How it will affect the answer? Because it can have answer like this as well. If I draw one vector and I drew the same length, so we can have a resultant like this as well. So the length is important when you consider, length is also important. Is it clear, this question? So these are some questions related to topic momentum. Why did you reverse the direction of? I did not reverse the direction. We took the question was calculate the change in the velocity. So if we need the change in the velocity is final minus initial. So we drew the final, this is final, this is initial, but we don't draw initial, we draw negative initial. Why? Because the change in the velocity is always the final minus the initial. That's why when we join from tail of the first to the head of the last. That will be the change in the velocity, which is final minus initial. So this was topic momentum. I'll share another link and discuss the doubts related to the weekly homework.